Please start.
Thank you very much, and thank you very much for giving me this opportunity to give this seminar talk here. So, yes, what I will talk about is basically kind of a combination of independent component analysis, so ICA on the one hand, and deep learning on neural networks on the other hand. In particular, what I will claim is that nonlinear ICA provides what I would call a principled framework for unsupervised kind of deep learning. And, well, technically, the important thing here is that it's really only possible in some sense when we use the temporal structure of the data. So the basic problem is extremely well known. Unsupervised learning, unsupervised feature extraction, we have multidimensional data where there are no labels. So importantly, what we will do here is to use the temporal structure in time series, not just for fun, but because as I will explain, we actually have to do it, have to use the temporal structure to properly do something like ICA. I will actually present two different methods which use the temporal structure in two different ways. And thus, actually, although these methods are in principle initially motivated completely heuristically, the main point here is to show that these two methods actually provide two classes which are two classes of nonlinear ICA methods which actually estimate nonlinear ICA in a specified sense, and thus what we also have is two definitions of nonlinear ICA which are provably identifiable. I will define that term a bit later. So thus we get a new principled framework for unsupervised deep learning in the sense that we can actually prove that we get what we wanted in the first place. So, well, yes, unsupervised learning is, of course, well, people would agree it's a largely unsolved problem as opposed to supervised learning where you just do backpropagation or something. And it's, of course, important because labeled data is often costly or almost impossible to obtain. And so my approach here is based on probabilistic models with latent variables, which I'm a bit repeating myself, but my claim here is that it's a powerful principled approach, principled in the sense that when we have the latent variables, and we want to recover the latent variables, we actually have a well-defined goal. So now going back a little bit in history, ICA in the linear sense is basically what I would call a case of principled unsupervised learning. So here's the basic definition, rather well known, of linear ICA. So we have observed variables xi, where t is the time or some other sample index, and they are modeled basically by a linear superposition of certain latent variables sj, where the number of these latent variables is typically assumed to be equal to the number of observed variables. And then the practical difficulty here is that, well, the observed variables are not equal to the latent variables in any. We don't know the connection very well. We only know that there's some kind of we know that there's a linear mixing which basically mix up all the independent components to give us the observed variables. And the goal here is, because it's unsupervised learning, it means that we only observe the x's, not the s's, only the x's, and then the goal is to recover the s's, both the s's and the a's, given only the x's. And the fundamental theory of ICA says that this is actually possible if we assume that these independent components, also called sources for simplicity, are statistically independent and non-Gaussian. This was actually basically proven by Darmois and Skitovich around 1950, but then rediscovered by Como in 1994, which was then actually part of the ICA boom in the 90s. So now this is what I call identifiability, or what people call identifiability in this field. It means that, well, the model is well defined in the sense that when we observe only the x's, we can actually recover both the a's and the s's in the limit of infinite data. So in other words, the original sources can actually be recovered from the observations of linear mixtures, importantly under the assumptions of independence and non-Gaussianity. Now, actually, before going further, perhaps I must have a short digression on the question of what is actually the goal in unsupervised learning. I think there's a lot of different opinions on what is the goal of unsupervised learning, and this leads to kind of unnecessary debates where somebody proposes an unsupervised learning method with one goal, and then others criticize it because it doesn't reach the goal that they are interested in. So I have here a list of perhaps 4 different goals of unsupervised learning. First one would be to obtain an accurate model of the data distribution in some probabilistic sense, for example, by having a small Kullback-Leibler divergence between the model and the data distribution. Another goal, which is very fashionable recently, is to provide a method that samples points, new points, from the data distribution. This is then a little bit more difficult to evaluate. Often people do this with images and then generate new images and then just show them. On the other hand, of course, a very old goal in unsupervised learning is that you want to find features which are useful for supervised learning. So in this sense, then unsupervised learning is only useful to the extent that it helps supervised learning. And well, whether you have reached this goal can of course be then evaluated by calculating taking the features given by unsupervised learning, inputting them into some simple classifier using some benchmark data, and then looking at the classification accuracy. On the other hand, one goal has always been to somehow reveal underlying structure in the data, something that's hidden in the data. I will have a couple of examples of that later, and that we actually want to recover. Something like separating sources. In this case, the evaluation may be quite difficult for real data. Often what we do is that we show the results to an expert on that data domain and ask his or her opinion. So my point here is that these criteria are quite different, in some sense rather orthogonal or even contradictory, some of them. For example, I would say that the goals 1 and 2 are essentially kind of non-parametric problems. Number 1, for example, could perhaps be best solved by some kind of a kernel density estimation if you had an infinite amount of data. While if you use a kernel density estimator, you will not obtain any kind of features, you will not in any way go towards goals 3 or 4, and you will not get any information about some kind of underlying structure in the data. So I think when we do unsupervised learning, it is important to be more specific and define your goal more specifically. So what I'm doing here in this talk, and actually what people mainly do in ICA, is to try to work towards goal number 4. That is, I will try to find some kind of underlying structure in the data. I'm not interested in sampling points or not even having an accurate model of the distribution. I'm really interested in finding some hidden underlying structure in the data. Okay, well, now if you look at classical well-known applications of ICA, I think we see some examples of this, especially the goal number 4, that is find underlying structure in the data. For example, you can do ICA on brain imaging data, EEG or MEG data. Here we have, or fMRI data. Here we have MEG data, which is a bit like EEG, but a little bit better. And now if we do ICA, here's basically 9 ICA independent components selected by some stability criteria. And I will not go into details, but the idea is that, well, actually many of these components correspond to well-known sources in the brain. Some are sources in the visual cortex, others in the somatosensory cortex. And if you show this to an expert, they will say that, well, yes, at least some of these are plausible. And then if some of them are plausible, maybe the others, which are not at first sight plausible, maybe they will actually then reveal something completely new about this kind of a data. So here, really, I mean, if you just did like a kernel density estimator and got an extremely good estimator of the density, that wouldn't actually help you at all. We really want to find the kind of hidden structure in the data. Another well-known example is image feature extraction. So here, basically, we have input small image patches to an ICA algorithm. The features, each small square here is one feature. Well, I will not describe them in any detail, but we see features which are similar to wavelets, Gabor functions, or simple cells. And again here, now, what is important, I think the most successful application of this kind of an idea is really on computational neuroscience, modeling neurons in the visual cortex. And then, well, it is really a question of finding some kind of a well-defined hidden structure in the data. It's not, if you just had some kind of a non-parametric estimate of the density, that wouldn't give you any kind of anything, that wouldn't tell you anything meaningful about some kind of an optimal visual processing. Okay, and just I will briefly show this idea that we had earlier, topographic ICA, where you basically have build a probabilistic model that at the same time orders these features in a nice topographic, spatial organization. But okay, so the basic, the point that was kind of early background in some sense. Now the question is that could we actually do nonlinear ICA? Well, nonlinear ICA is really an unsolved problem. And it's actually very difficult. If we just try to, in a very simplistic way, extend linear ICA to the nonlinear case, it just doesn't work. It doesn't work in the precise sense that the model is not identifiable. More precisely, if we simply replace the mixing system by some arbitrary nonlinear mixing function, perhaps invertible and smooth, and say that the x's are some invertible and smooth, the vector x is in an invertible and smooth transformation of the independent components, well, then it is simply not possible to recover the original sources, which was actually originally proven again by Darmois, 1952, although we in some sense rediscovered the proof a little bit later. Now, one way of understanding this result is that if you have two random variables, x1 and x2, then you can always find a function g of x1 and 2 so that it is independent of one of the variables x1. So basically you can choose any of your observed variables and you can always find something that's independent of it. So in that sense we can see that, well, the independence itself doesn't actually allow us to recover the original components, especially because instead of x1 or x2 you could actually take any nonlinear transformation, any function of your variables, and then you can always find another function that is statistically independent. So this is really kind of catastrophically non-identifiable. We cannot actually find the original sources. Here's a graphical illustration that I will use later as well. We have here two sources plotted in kind of, the color here is simply for illustration. Here's the distribution of the two sources or independent components. Here's a very nonlinear mixture of those two. And now using the construction actually proposed by Darmois, we can find two variables which are independent. But clearly you will, well, graphically I think you will clearly see that this distribution here is very different from this one, and we didn't find the original independent components. But the underlying assumption here is that we are only looking at the marginal distribution over time, or some other sample index. Maybe t is not time, maybe it is some other kind of a sample index. But if you actually break this assumption and use something else, maybe then we can proceed. So maybe actually temporal correlations would help us in finding ICA. This was basically already suggested by Harmeling and others in 2003. Well, the basic idea is that, well, given the observed variables, so here like 3 signals, we try to transform them. Well, this is a gross oversimplification, but in some sense we try to transform them so that the two signals which are maximally stable, that is maximally slow, maximally correlated over time, which has been proposed in a kind of a vision research literature under different names, originally by Föld-Diak as a principle for finding invariant features, and then popularized by Wiskott and Sejnowski under the name slow feature analysis. So now the question is that does this actually work? In other words, is this identifiable? Can we identify the original sources by this method? Well, in the linear case we know that yes, we can. I mean, that is, of course, that was the motivation for Harmeling and others to propose it as a nonlinear extension. Although there's a little bit of maybe a little bit an unpleasant assumption that you have to make on the correlations of the sources, but still fundamentally it kind of works. In the nonlinear case, well, we don't really know. Harmeling and others, they didn't prove the identifiability in any way. The simulations were rather encouraging, but also the method contained some hacks, and it is not very clear whether we can draw any very general conclusions out of that. In fact, in the literature of ICA, there have been various kinds of temporal structure used for source separation. Well, mainly actually two different kinds. One is the kind of autocorrelation stuff that I just mentioned, but the other one is non-stationarity. The idea here is that, well, if the sources are non-stationary in a suitable way, then we can actually use that as a separation principle, so that basically we kind of, again, transform the observed variables to new variables which are kind of maximally non-stationary, and under certain conditions, well, that actually separates the signals. Non-stationarity is, of course, a very general concept, but here what people talk about is usually some restricted forms of non-stationarity, in particular the non-stationarity of variances, where we assume that kind of the variance of a Gaussian variable is smoothly changing as a function of time. Actually, surprisingly, many different kinds of data sets have this kind of non-stationarity. You can find it in video data, in speech data, e.g. MEG data, and financial time series. So, as I just mentioned, well, this model is also identifiable. This kind of a system can also be, this principle also allows separation of sources in the linear case, actually without any particular stringent assumptions. In the nonlinear case, well, again, we don't really know. There's not only is there no proof, but actually this kind of a nonlinear extension has almost never been attempted, really. Okay, so what I'm going to talk about here is two methods for nonlinear ICA. These two methods extend the linear separation principles meaning separation principles for linear ICA that I just mentioned, in particular the idea of temporal temporal dependencies and the principle of non-stationarity. Now, what both methods have in common is also that we actually implement them by using logistic regression in a neural network with artificially defined labels. So in some sense, we are turning the unsupervised learning problem into a supervised learning problem by defining certain labels artificially. This is the same kind of an idea has been previously used in noise contrastive learning as well as generative adversarial networks. And importantly, although in the beginning, I will introduce the methods from rather heuristic, with a rather heuristic motivation. But actually, then what we can do is that we can analyze these methods, and we can prove that they will actually do separate the nonlinear. They do separate sources which are nonlinearly mixed, which means that we actually have a constructive proof. Well, actually, two constructive proofs, one for each case, of identifiability for nonlinear ICA. So basically there's two different things here. One is to show in general that these forms of nonlinear ICA are identifiable, and second, to propose the algorithms for separating them. Although of course we do both of them at the same time by basically proving the convergence of the algorithms. But the point is that even if you don't like the algorithms, still the proofs of identifiability are valid, and in particular the definitions of nonlinear ICA that we present here should be interesting for further, maybe you want to develop your own algorithms for those models, for example. Okay, so the first method is called time contrastive learning. Here the intuitive idea is very simple. We basically learn features that enable discriminating data points from different time segments. So we use ordinary neural network training where the last hidden layer gives the features, and then we prove this rather surprising theoretical result, at least it was quite surprising to me, that actually this heuristic method estimates a nonlinear ICA model where the observed data vector x is a rather general arbitrary nonlinear function of the independent components, and importantly, these independent components are non-stationary. So, in more detail, the intuitive principle is as follows. So we observe an n-dimensional time series x indexed by t. Okay, what we do is that we divide this time series into big T segments, rather large number of segments, in the basic case just taking bins or segments with equal sizes. And now then we train a multilayer perceptron to tell for each single data point which segment it comes from. So basically we have a classification problem where the number of classes is big T, that is the number of segments, where the label of the class is simply given by the index of the segment, so given in different colors here. And then basically the learning is simply ordinary, completely classical multinomial logistic regression in a neural network, which we can neural network we can conceptually divide into two parts. One is the feature extractor, which is basically everything up to the last hidden layer, and then a last layer, which is basically linear, given by the multinomial logistic regression, and of course the softmax function. Now, intuitively, you would think that in the hidden layer, the multilayer perceptron should learn to represent the non-stationarity. Because, well, non-stationarity is really nothing else than the distribution, non-stationarity is really nothing else than the differences in distribution between the different segments. So if the MLP is to be able to classify, discriminate between different segments and tell for each data point which segment it comes from, then what it exactly has to learn is the difference of the distributions between the different segments. Okay, so that's basically the principle. That's basically the algorithm. So now we can actually analyze the algorithm, and we have the following theorem, which basically says that time contrastive learning estimates nonlinear non-stationary ICA. So let's assume that the data follows a nonlinear ICA model, x equals f of s, where the mixing is quite arbitrary, just smooth and invertible. And the independent sources are non-stationary in a certain way. In the basic case that I'm considering here, they have non-stationary variances, as I defined a couple of slides ago. And then assume we apply time contrastive learning, as I just described. That is logistic regression to discriminate between different time segments, where we use an MLP, where now the hidden layer has the same number of units as there are observed variables. Then we can prove, well, that takes like almost one page to prove, but actually it's a reasonably simple proof. We can prove that the squares of the independent components are equal to some unknown linear transformation of the outputs of the last hidden layer, where the squaring is simply element-wise. So basically what that means is that TCL demixes the nonlinear ICA model up to some unknown linear mixing and up to the squaring here. But this linear mixing can usually be estimated by linear ICA. So we are only actually left with the squaring. In the paper we describe some special cases where even the squaring might actually be resolved, but hopefully in many applications it is actually not quite necessary to resolve it. So what we then have is a constructive proof of identifiability of the model, at least up to this squaring. Okay, yes, well, this was the basic case. We actually have a generalization of the theory, where instead of looking at non-stationary variances, we look at non-stationarities inside defined by exponential families. That is, we have an exponential family with an arbitrary number of sufficient statistics, and then basically the parameters in the exponential family are changing from one segment to the other, and that is what creates the non-stationarity, which is of course a generalization of the non-stationary variances in a Gaussian family, which is one very special case of exponential families. We also prove in the theorem, we prove in the paper that the method can also be used for dimension reduction, so which is certainly very useful in practice. In practice, we would usually want to have a smaller number of units in the hidden layer than we have observed variables, and we show that this is also kind of a principled thing to do. And thus we get something a little bit between nonlinear ICA and nonlinear PCA.
What if you don't know the number of sources?
Well, that's always the problem in ICA. So even in linear ICA, it's really an old problem, and nobody has a really good solution for that. So what people usually do is they just try to guess it. And well, for real data, it is quite possible that you actually get reasonably meaningful solutions even with different numbers of of sources that you try to estimate.
Do you tend to get some meaningful components and some useless components when you overspecify, or do they tend to mix up completely?
I think that would be the hope, yes. Of course, in real data, it's usually, it just changes smoothly, so, and you may not know actually the ground truth anyway. So what usually happens when you apply it on real data is that, well, some of the components are really nice, then you start getting a little bit the components which are a little bit more difficult to interpret, but you don't know, they might still be quite meaningful. And perhaps when you increase the dimension too much, then, well, it may be that, well, then the last components are clearly bad. But on the other hand, it may also sometimes happen that then you are kind of increasing, perhaps you are increasing the PCA dimension of your data too much, and then everything starts getting a little bit more noisy. That may happen. On the other hand, if you do like images, if you take do image decomposition, then, well, you can try different numbers of principal components and then do ICA in that subspace. And for almost any dimension, you actually tend to get meaningful results. And somehow the method almost doesn't break down at all. Yeah, so yeah, well, that, well, image feature extraction is, of course, something where the features are not exactly that well defined, as opposed to something like EG or MEG, where I think we can often talk about like reasonably well defined physically and physiologically reasonably well defined components.
Question?
Yes.
How does the length of the time segment affect this in practice?
Well, that is basically kind of a free parameter here that it may be a little bit like the PCA dimension, which usually is equated as to the number of components. So that maybe in practice you have to just try out different numbers. Although we have, at least in some simulations, we have found that, well, basically you could just try to find the length of the segment that gives you the best classification accuracy. I'm not sure if that works in general, but at least in some simulations it seems to work. But that's a little more like an open question. At the moment we are just thinking that, well, perhaps based on some a priori knowledge, you can fix a reasonable length of the segment. Okay, so here's an example of applications. I have to check the time, so, okay, there's a clock there. Okay, yeah. Yeah, so what we did, we applied this on MEG data, where on resting state data, which is kind of a very fashionable thing to do in brain imaging data. So you just measure people when they are sitting in the scanner without any particular task or any particular stimulation. So then you actually get automatically an unsupervised learning problem. You just have the brain imaging, you just have the brain scans, or well, yeah, brain activity, and no labels really. So we applied the nonlinear ICA method on that kind of resting data, but then for validation we took data which was from the same subjects, but this time with different kinds of labels given by stimulation modalities. There was visual stimulation, auditory stimulation, and tactile stimulation, and then also rest periods in between, which gave us basically 4 different classes. And so then what we did is we trained a linear SVM on the sources estimated by TCL with MLPs of various depths, and then looked at the classification results. So here kind of validating unsupervised learning by looking at how useful it is from the viewpoint of supervised learning. Yeah, so the main results are really here. So here's the classification accuracies for TCL, and then for various competing methods, denoising autoencoder, then the method by Harmeling and others, and a linear ICA method. So what we see is that, well, TCL basically works better, but also importantly what we see is that when we increase the number of layers, we get improvement in the performance. L equals 1 would actually correspond to linear ICA, but we see that when we introduce nonlinearity, we get increase in the classification accuracy. So this would indicate that nonlinear ICA is actually better than just linear ICA. Although, of course, it's true that the difference is not that big on this kind of data. And then, of course, we could try to visualize the nonlinear processing by looking at how in the different layers you kind of pool information from various kinds of, from various parts of the brain. But, well, that's, of course, really difficult, as we all know. Visualizing or interpreting what a neural network does is extremely difficult. So maybe I don't go into details. Okay, so that was the first method, time contrastive learning, and now then the second method, permutation contrastive learning. Here, the idea, we again formulate a classification problem from a completely intuitive viewpoint, and then we show how it works in how it estimates nonlinear ICA. So here we formulate a classification by saying that we learn features that enable discrimination of two kinds of data. One is short time windows of the real observed data versus short time windows of data where we have completely time shuffled the data, so permuted the temporal ordering of the time points, thus destroying the temporal structure. And again, we do ordinary neural network training where the last hidden layer gives the features. And again, I claim the theoretical result is surprising, at least I found it quite surprising, which is that, well, this kind of a method can actually be seen to estimate a nonlinear ICA model, where just like earlier, just like in the previous method, we have a general nonlinear mixing. The observations are general nonlinear mixing of independent components. But now the statistical assumptions on the temporal structure are different. Here what we have is components which have temporal dependencies, and they are stationary, as opposed to the non-stationarity earlier. So, in more detail, again we observe an n-dimensional time series. So, of course, we have to, in ICA kind of a context, we always must observe a multidimensional time series, a multidimensional data. Otherwise, for one time series, well, for one-dimensional data, it doesn't work. And then we take short time windows as the new data. In the very simplest case, we take just time windows of length 2, so just two time points next to each other. And then we create this artificial time-permitted data where we take windows of 2 data points, but from random time points, so that basically we destroy all time structure. There are no time dependencies in this data, but the marginal distributions are exactly the same as here because we take samples from the same XT. Okay, and then we simply train a multilayer perceptron to discriminate between these two datasets, real-time windows versus time-permitted time windows. So it's nonlinear logistic regression with just 2 classes, again using a neural network, which has some structural constraints, some kind of what they call, I think, Siamese structure over time, which simply comes from the fact that, well, the mixing is the same for all time points, and so the same mixing is kind of applied twice on these 2 time points. And again, we look at basically the outputs of the last hidden layer, which we consider the feature extractor and the estimate of the independent components. And, well, okay, before going to the actual theorem, we need to introduce a couple of definitions on the temporal dependencies of the independent components. So, for simplicity of notation, let's denote one independent component at time point t as x, and then by y the kind of the previous time point. And let's look at the cross derivative of the log PDF of those 2 subsequent time points. Now we define that the random vector is quasi-Gaussian if this cross derivative can be expressed as in a factorized form where we have the same function of x as we have of y. And then obviously we define that the time series is quasi-Gaussian if this is true for all possible windows. So this is actually equivalent to saying that the log PDF has the following kind of structure. We have a function of x plus a function of y plus a product of the same function of x and y. So now we see here that this is something that's kind of similar to a Gaussian case. In the Gauss, if the time series, if the vector xy were actually Gaussian, then of course we would have here linear functions, and here we would have quadratic functions. So it's a generalization of Gaussianity. Then we also define a stronger form of dependence, saying that xy is uniformly dependent if this cross derivative is non-zero for any x and y. Now, independence would say that this has to be identically zero, and so dependence, just an ordinary definition of dependence would say that Q has to be non-zero in any set of non-zero volume. But so here we are saying that it's non-zero everywhere, so it's really a stronger form of dependence. But I think actually that this condition may not be necessary. It's just in the proofs, I wasn't able to prove the theorem without this assumption, but it may not be necessary, while quasi-Gaussianity is definitely necessary in the following theorem. So,
zero somewhere on zero measure set?
Sure, yes. Although, well, no, sorry, no, it cannot. No, not in these proofs. Again, I think we could prove it in that kind of a case, but in these proofs, I tried hard to prove it in that case, and I think it's probably possible, but I wasn't able to make it. So I had to actually make this strong assumption, which I do find a little bit annoying. I hope, well, somebody finds perhaps a better form of the proof. Okay, so the theorem says basically that, again, we assume that the data follows a nonlinear ICA model with same kind of a mixing system, a smooth invertible nonlinear mixing F. But then we make the following assumptions on the independent components. First of all, obviously, we assume that they are independent over I, so different components are statistically independent, and they are stationary. Of course, stationarity is kind of a default assumption. The reason why I'm saying it here is simply because we had the non-stationarity in the previous theorem. And then we use the two definitions I had on the preceding slide, that is, we assume that all windows of independent components are non-quasi-Gaussian as well as uniformly dependent. So it's a little bit a stronger condition than just saying that they are non-Gaussian, which is quite typical in ICA, and also a stronger assumption than just saying that there are some kind of a temporal dependencies. And then we assume that we apply permutation contrastive learning on this, as I just described. That is logistic regression to discriminate between real-time windows and time-permuted time windows, using an MLP where, again, the hidden layer has the same number of units as the number of dimensions. And then what we can prove is that actually the independent components are given by the outputs Hj of the hidden layer units up to certain scalar, actually invertible scalar and invertible nonlinearities Ki. Now this kind of a indeterminacy with scalar invertible nonlinearities is kind of natural, and somebody might say almost unavoidable, because after all, if we take just some invertible scalar nonlinearities of each component separately, then they will still be independent and they will still have time dependencies. So there's, in some sense, it's almost impossible perhaps to recover this kind of a final nonlinearity. It's a little bit like in the linear ICA case, where there's always a kind of a multiplicative constant for each independent component, which is simply not defined and which we cannot determine. Okay, so we actually get something quite nice. In the previous theorem, we had the kind of some unknown linear mixing, but here we don't even have that, so we really get the independent components. Nor do we have anything like squaring, like in the previous theorem. So basically, then we have proven that PCL mix is nonlinear ICA, and again we have thus a constructive proof of the identifiability of the second ICA model, briefly defined here. Of course, in the paper there are more details. Okay, and here then the question is that what happens if the sources actually are quasi-Gaussian. Now, in the basic linear ICA case, we know that if the sources are Gaussian, then, well, we are kind of, we can't really do anything. But in the time-dependent case, actually, even Gaussian variables can be separated under certain conditions. So it's actually interesting to see what happens in the quasi-Gaussian case. Actually, we can prove that for quasi-Gaussian sources, including the case of Gaussian sources, actually the PCL will demix the nonlinear mixing up to a linear mixing, up to an unknown linear mixing, just like in the case of the previous method. And then if you make some further assumptions, perhaps you can actually even estimate that linear mixing. Right. Okay, so here's an illustration of how that works. This is the same, in the beginning we have the same data that we had on the previous slide. So now as a kind of a non-Gaussian and non-quasi-Gaussian process, we use a Laplacian autoregressive model. So each of the components is created by an autoregressive model with some autoregressive coefficient and Laplacian innovations. Oh, sorry, there must be a minus sign missing here. And the nonlinear mixing is simulated by a multi-layer perceptron where we use leaky rectifying linear units to make it invertible. And yes, the number of units in each layer is also the same. And in the demixing is also modeled by an MLP, but this time with more flexible nonlinearities given by the max out. So the data is actually the same as earlier. So we have two independent components and a highly nonlinear mixing. Now our method basically gives you this. I think you would agree probably that it's a reasonably good estimate of the original distributions here. While here we have the result from the method by Harmeling and others, which really doesn't work that well. If you look at like the colors, they are all like in a little bit wrong places. So the yellow is here while it should actually be here, and so on. And to analyze this in more detail, now we have here scatter plots of the original independent components versus their estimates. So in our method we see that, well, really we have something like an invertible nonlinear transformation plus obviously some estimation errors for both of the two independent components. While in their method then, well, the scatter plots are rather bad, well, maybe even, well, yeah, well, let's just say rather bad. Right. Yes.
So both methods can only estimate up to scalar transformation, scalar invertible transformation.
Exactly,
right?
yes.
So when you do the evaluation, you have to somehow account for that uncertainty.
Yes. So that's why I'm just plotting the scatter plots here. So ideally then the scatter plot would be this, would give this scalar nonlinear function, but like kind of a sharply without any kind of noise.
So you don't expect it to be a straight line?
No, I don't. No, I don't. I expect it to be a nonlinear, any kind of a nonlinear scalar nonlinearity, but without kind of just without any deviations from that deterministic nonlinearity, with no noise, basically. While this here is obviously has a lot of noise. Oh, I don't know if noise is the right term, but anyway, yeah. Okay. Well, I have simulations, but well, you know, the simulations are reasonably boring, just showing that our method works and others don't work. So maybe I will skip them. I find this kind of results rather boring. Okay, and then I will just conclude. So we have basically here proposed two new methods for unsupervised learning. The first one was time contrastive learning, where the idea is that we divide a time series, a multidimensional time series, into segments, and then learn to discriminate data points, basically telling which segment each data point comes from. And then permutation contrastive learning, where we discriminate between time windows of real data, maybe very short time windows of real data, versus time windows where the time structure has been completely destroyed by shuffling. And so these are kind of a very intuitive learning principles that you could actually use in many kinds of data. And sometimes I wonder if somebody has perhaps proposed something somebody must have proposed something very similar from a kind of a just intuitive viewpoint. And the nice thing here is that the training uses simply completely ordinary neural network or deep learning algorithms and software. So we don't actually distribute any software. We don't really need to at all. But then the main contribution here really is to prove that these two methods estimate nonlinear ICA. So each of them estimates one specific form of the nonlinear ICA model. And these two forms of nonlinear ICA models are actually rather direct generalizations of well-known separation principles separation principles which are well known in the theory of separation principles which are quite well known in the theory of linear ICA. So basically the idea of non-stationary sources for TCL and time-dependent sources for PCL. And in both cases, now this is important, in both cases we solve the problem with quite general, just smooth and invertible nonlinear mixing functions. Of course, a completely different approach to this problem would be to restrict the form of the mixing function. That's somehow what I don't want to do. I would rather make assumptions, statistical assumptions on the components and just let the mixing be anything as general as possible. But certainly it's an interesting research line which has not really been pursued by almost anybody to successfully to try to be able to solve nonlinear ICA by restricting the space of nonlinear mixing functions. But so what we get is basically the first cases of identifiable nonlinear ICA, identifiability meaning that we can actually recover the original independent components up to some very weak, perhaps trivial indeterminacies. And thus we arrive at the kind of the fundamental, the basic claim here, which is that this is kind of a new principled framework for unsupervised deep learning. This is something where basically we can validate our methods from purely kind of internal theoretical criteria, which has been done. This has been done in almost all the classical literature on ICA. So basically, you generate data which follows the model, and then you can evaluate different algorithms depending on how well they actually recover the independent components. Right. Okay, and for future work, I suppose I should mention that in some sense, the methods are kind of screaming for being applied on image or video data, where presumably we would get very interesting, perhaps rather high-level components from using completely unsupervised training. Possibly we would get features which are rather similar to what people get these days with ImageNet, but we wouldn't need any labels. And thus also we would be able to use huge amounts of data, and also, which also allows then us to use very high dimensional data and so on, and large number of features. And from a theoretical viewpoint, what we would like to do is to combine these two methods, TCL and PCL, so that we get a single method which somehow uses both of these two different kinds of temporal structure, and thus would be very general and perhaps also statistically very efficient. Okay, thank you very much.
Maybe one pointer to related work on images is a CVPR paper from 2015 where it's applied on images from Alyosha Afro's group. They take a 3x3 grid of image patches and they set up an auxiliary prediction task which is given the center patch, and one of the 8 neighboring patches learn which one of the neighboring 8 patches it is. And they use this for unsupervised representation learning. As you said, it gives features as good as ImageNet, but of course using empirical motivations and stuff, so it's not like with a nice theorem or something, but it's maybe an interesting work. But in that work, what they had to do is they had to take out, in this grid, they had to take out some spacing in between the grid cells, because the task would be much too easy if you get to see 2 adjacent patches. And in your method, in the permutation contrastive learning, as you presented it, you don't take out some time in between. So I imagine if you have a time series which is slowly varying, it would be very easy. You just take a small one finite difference feature at the very beginning of this swapping block, and you can detect whether it has been swapped or not. Can you comment on whether that's a problem, whether that's a feature the neural network will pick up?
Yes, some people have actually commented on that, saying that, well, it's important that this kind of a classification task would not be too easy. I suppose it's probably a valid point if we apply this on something like video data. We haven't applied this yet on video data, so I cannot yet say anything about whether it would be a problem or not. I suppose then it's a question, perhaps it may be possible that we actually need to use some tricks like that to actually make it, to make the classification task difficult enough. Then of course there's a number of parameters here, like, well, the length of the segments in TCL or the length of the window in PCL and so on. And presumably, yes, we would need to somehow figure out such values of the parameters that also the classification task is not too easy. Yes, I think that is probably going to be a valid point in practical applications, yes. Yes, thank you.
So I had a couple of questions, but one is, you seem to have a very general recipe of you define first what the interesting property of the sources are, then you mess it up and try to contrast the original signal versus a messed up version. Can you, do you have ideas about other measures, other interesting properties of the source signals outside non-Gaussian, non-stationary?
Well, so in the theory of linear ICA, we really have basically three separation principles. One is non-Gaussianity, which doesn't work for nonlinear ICA, and then we have a temporal dependencies, usually simply used in the form of autocorrelations, and then we have the non-stationarity. There's a couple of a couple of proposed principles which have been almost never used. Something like cyclostationarity, for example, which is, I think, very specific to certain kinds of data. But really, in the theory, in the linear ICA theory, we almost always operate with the three separation principles. So, in some sense, we have now exhausted all of them. We have theory for all three of them. So, yeah, I've been trying to think whether we could actually find some other forms of temporal structure that would enable separation. But it seems to be a rather difficult problem, because if they did exist, then perhaps people would already have found them in the linear, probably people would have found them in the linear ICA literature. But it would be really, really interesting if you could find a new kind of a form of temporal structure or something which enables separation and which is general enough. But I really don't know what it would be. From a practical viewpoint, I think what we would really need is to probably combine these two properties. Look at the same time at non-stationarities and temporal dependencies.
Well, I have kind of two related questions. One was, so in linear ICA, we often estimate the number of components. Sorry to go back to that, by some tools from PCA, but with nonlinear ICA, it wouldn't be clear that those kinds of estimates would give you a good value for the number of components you should fit.
Sorry, but I didn't get the last sentence.
So the estimates of the number of components you need for linear PCA might not be good for nonlinear ICA.
Yeah. So
what kind of heuristics do you use in that case?
I mean, I think I never trusted any methods for estimating the number of components, PCA components, in the principal components, even in the linear case. I think they often give quite bad results. So that's why I always consider the number of principal components as something that you just have to you just have to try out different numbers and see which one gives the best results in practice. So I suppose logically, then I wouldn't trust any methods. at least I'm not aware of any really good methods for then estimating the nonlinear dimension of the data either. I would probably just so in practice, yes, in practice, as I said in the case of TCL, we actually have basically a theory that talks about the dimension reduction in the sense that, well, we are showing how it actually makes sense to have a smaller number of units in the hidden layer than smaller than the number of observed variables. A similar theory might perhaps be developed for PCL, the other method. I just didn't actually. I just didn't do it. I never occurred to me that, well, maybe I should do it. But I suppose in practice then, when you apply these methods, either of these methods on real data, you may not want to use the same number of hidden units as the number of observed variables. That's just, the theoretical simplification. In practice, you would probably want to have perhaps even a very much smaller number of hidden units. And again, so I don't quite know whether there's any, well, at least we don't have in the papers any, we don't discuss how to choose the number of hidden units. I suppose you could probably figure out some heuristic methods for choosing that, perhaps again related to what gives the best classification accuracy for test data or something like that. But I don't have any kind of a really good theoretical way of proving that, and in practice I would probably just try out different numbers. Just like in linear ICA, I would just try out different numbers of principal components, and here I would probably just try out different numbers of hidden layer units. I'm a little bit skeptical about finding a theoretical method for that, but maybe it's possible. Yeah, I don't know.
So the capacity of the neural network that you use for discrimination, if that becomes smaller and smaller or deteriorates, and you can't express the true conditional probability, then what happens? Does the proof degrade in a way, or do you have an understanding of how the separation degrades, or what happens?
Well, the proofs are all based on the completely ideal conditions, so that we basically use the universal approximation capability of the neural networks. We are assuming that we are actually able to approximate any functions, and also we are assuming that we have an infinite amount of data. Now, I don't really have any clear idea on how to analyze the case where we don't have the universal approximation capability. Of course, not having an infinite number of data points, that's classical. You calculate the asymptotic variance or something like that, and widely done in linear ICA. But well, if we don't have universal approximation capability, I have almost no idea what to do. This is actually something which, in some sense, people are these days putting a lot of energy into analyzing what kind of functions neural networks are able to calculate and how it is possible and so on and so on. But I'm just completely skipping all that discussion and saying that we have the universal approximation capability. And that also means that, in fact, these theorems are not, or these methods, the methods or the theorems are not in any way restricted to neural networks. We just need to have some kind of a function approximator that has universal approximation capability. I assume that some kind of a kernel machines would also work, although I don't know exactly.